So, welcome everyone to the 13th and last seminar for this semester. For the year, we've had, I think, about 18 guest speaker lectures, and it's been a wide variety of speakers from Canada to England, topics on neuroscience and theology to time, quantum time crystals, to pathogenic proteins, agrichemicals, molecular glues. It's been fun. All these topics and all these different personalities that we've had a privilege to learn from, and illustrates that chemistry is everywhere. Chemistry is in everything. And this afternoon, we will hear about something I didn't know about here, programmable catalysis, an introduction. We'll hear about that here pretty soon. Before, I would like to introduce my co-host for today, Janelle Green. She's actually taken OChem lab course with us right now, and she's actually making some really cool, doing a really cool project, making a rare type of azo dye. She's a senior mathematics major with a chemistry minor. She plans to attend medical school after graduation. She went to high school at Shenandoah Valley Academy. And she's actually completed math research with Dr. Bozeman on knot theory. And she's moved all over the United States and Japan. Her dad is in the US Air Force. She currently lives in Berrien Springs, but has lived in several US states. What are some of the states you've lived in, Janelle?
Virginia, Massachusetts, Texas.
No Minnesota?
No,
Okay. All right. Her hobbies includes knitting and crocheting. Seems like she's picked that up of late. So Janelle, go ahead and introduce our speaker for today.
Okay. Our speaker, Paul Dauenhauer, received a Bachelor of Science in Chemical Engineering and Chemistry from the University of Wisconsin-Madison in 2004, and a PhD in Chemical Engineering from the University of Minnesota in 2008. From 2008 to 2009, Paul worked as a senior research engineer for the Dow Chemical Company.
Hmm.
2014, he is the Lanny and Charlotte Schmidt Professor and MacArthur Fellow at the University of Minnesota in the Department of Chemical Engineering and Material Science. His work has been highlighted with the National Science Foundation Career Award, the Department of Energy Early Career Award, the Camille Dreyfus Teacher Scholar Award, and the American Institute of Chemical Engineering CRE Young Investigator Award. In 2020, he was selected as a MacArthur Fellow. His published patent applications serve as the scientific foundation of 5 startup companies, including Ceronics Renewables, Lacroll Technologies, Carba, Activated Research Company, and Onverd LLC. I invite Dr. Dauenhauer to speak.
Thank you, Janelle. It's always great to talk to new people, people I haven't talked to before, and faculty love to talk about their research. So another chance is always welcome, and thank you for the opportunity. I'm going to talk to you about something we've started working on. I'll explain, a lot of the talk will be about why we're interested in this and the background and history, and that has to do with this picture I show you. It's not just a cool picture. I mean, it is a cool picture, but it actually connects to the science and engineering that we're going to be doing. So let me just jump right in. If there's any issues, just let me know. There's a really great book that I read many years ago called The Alchemy of Air, and it goes through some of the history that I'm going to talk about here, which is more than 120 years ago. There was a meeting of the British Academy of Sciences, and you can see here this quote from the president, Sir William Crookes. He said, "If nothing is done soon, great numbers of people, particularly in the world's most advanced nations, were soon going to begin starving to death. As mouths multiply, food sources dwindle, and humans will begin dying in large numbers sometime around the 1930s." And what they were doing was projecting out the production of food and the population and seeing that there was a impending food crisis 30 years into the future for how much they could manufacture for the cereal crops that they needed. And the problem was actually very simple. Common foods that we use require a lot of fertilizer, and a big one being something like nitrogens, because plants and animals need nitrogen to make proteins or enzymes. Nitrogen can be made slowly by microorganisms. So some types of legumes will actually make it, like soybeans will. But really, you're not going to get enough of it. That's why we do crop rotation between corn and soybeans. But really, the only solution we really have for really aggressive crops like corn is nitrogen fertilizer. And in 1898, there wasn't a huge source of nitrogen fertilizer, particularly in Europe where those people were located. And so people were doing things like pouring urine on fields, collecting manure, spreading that as much as possible. But at the end of the day, the quality of the soils was degrading, and so was the ability to produce food. And this was an existential crisis because so many people needed this to survive. Let me back up here. Okay, so what was a solution? A solution was, well, we got to find nitrogen somewhere in the world. And at that time, it was known that on the western side of South America, there were large deposits of guano or bird droppings. You can actually see these old pictures of it. 1865, a 200-foot tall pile of bird dung was, of course, not a very pleasant idea, but it was very rich in nitrogen. And so, believe it or not, by 1865, that was the last year of the American Civil War. There were 300 ships per year that were going between England and Europe and Western South America, and all they were carrying was bird droppings, guano, for the purpose of agriculture, which is astounding to think about and horrifying to think that somebody had to work on those conditions. All right, so what's the problem here? So if you look at air, of course, is 80% nitrogen, 20% oxygen, roughly. I mean, there's other things in there, argon and things like that. And we need the nitrogen atoms in the air to make things like alanine, which we then use to make proteins. Now, why did I show a picture of lightning at the very beginning? It's thought that the origin of life was the lightning bolt, which broke apart N2 in the air and split it apart so that we could actually have single nitrogen atoms, which could then form proteins, which could then go on to form life. So that the idea that we have to break apart this very strong N3 bond or N2 bond, it's a triple bond, is a huge challenge chemically and in terms of the chemistry, and that has been argued as one of the key reactions from lightning. That's the origin of life. Now, of course, we have many different amino acids we use that get assembled into many different types of proteins, but we can't do that as humans. If we breathe air, we're not going to break down the N2 in the air. We need something to do it for us. And so, let's see here. Where's my computer? Okay, so this became an obsession over 100 years ago. How are we going to take the nitrogen in the air and break it down to something like ammonia that can form ammonia? Once it's an ammonia, we can put it into different products that can be used as fertilizer, and then these can be used in plants that go through animals and then eventually to us humans. Fritz Haber won the Nobel Prize in 1918 for the Haber-Bosch process, or the Fritz Haber chemistry, where he took nitrogen, combined it with hydrogen molecules, and over an iron catalyst, it split the N2 in half and formed ammonia. And that's a very famous, one of the most famous catalytic reactions. Like I said, it eventually led to him winning the Nobel Prize. Fritz Haber was a very interesting person. He did some great chemistry here, but he also was did some very horrible things in his life, including producing chemical weapons for the German military. He had a very complex life, but lots of good and lots of very bad things. Let's see here. So how does it work? Fritz Haber discovered that if he combines nitrogen and hydrogen with different metals, it breaks apart and eventually forms ammonia. And what happens is a series of events. So nitrogen in the air is made up of a triple bond. It adsorbs to a metal. I have some very simple words here because this is more for a lay audience, a couple of these slides. So when I say stick to a surface, what I mean is a process we call adsorption. So it forms a bond with the surface, it breaks apart, and then you have a single nitrogen atom right here. And then somewhere else you have hydrogen, H2, which breaks apart to form hydrogen atoms, and those add one by one. So you add one, then a second, then a third, and then it desorbs to give you gas phase ammonia. Now, the way this is done is very aggressive because to break this triple bond, you have to be at very high temperature. The commercial process, the biggest one in America is actually located not too far from you on the south side of Chicago, is a 400 plus degree C process because that's the amount of energy you need to break apart the nitrogen triple bond, even on a metal like iron. So, of course, this is great chemistry. Fritz Haber did this in a very small reactor, but Carl Bosch was a process engineer at a company called IG Farben, which you probably now know as BASF. This was 100 plus years ago. And what Carl Bosch had to do was take the reactor that was something, the size of a coffee can and turn it into something that would mass produce on a world-class scale ammonia. And his design was some of the most innovative process technologies in the world at that time to figure out how to do very high temperature chemistry, how to separate nitrogen from air at large scale, how to use hydrogen at incredibly high pressures. The pressures they're operating at were 200 atmospheres. And his contribution to the process here not only led to the development of the large-scale ammonia process and the nitrogen fixing process, but he also won the Nobel Prize in Chemistry for his accomplishments in separating N2 and turning it into ammonia. So what he had to do, though, was Carl Bosch's contribution is what we think of as the entropy problem. If you have a box on the left with three hydrogen atoms, or three hydrogen molecules and one nitrogen molecule, you're going to break those down to make two molecules of ammonia. And so you need to, and you're going to do this at high temperature, where high temperature forces the reaction backwards through entropy. So the solution to this by Carl Bosch was to operate his process at incredibly high pressures, 200 atmospheres. And to do that, he had to build reactor systems that would operate with high pressure hydrogen without the problem of metal embrittlement. And he figured all of this out. So now today, we have Haber-Bosch industrial process. They keep improving them incrementally, and we keep building more of them in the world, around the world. It's a high temperature, high pressure conversion of air into ammonia. It produces the world's fertilizer, all of the nitrogen we use for explosives and chemicals, and it saved the world from starvation. And in fact, I would say it went more. I mean, now the problem is not starvation. My problem I have is the opposite of eating too much. But what's amazing about this is we think about the place we're in right now, where we're worried about this existential problem of climate change. And the world went through something like this 100 years ago, and chemists, chemical engineers, material scientists all worked together to solve the problem. And I think we can do that again with climate change. So why are we talking about this important chemistry? Well, there's a lot of reasons. Let me back up a little bit. We have, like I said, this new problem of climate change, which is how we're going to deal with energy production while emitting CO2 or not emitting CO2. And what's happened is this massive energy transition. We're transitioning from large-scale fossil fuel power plants on the left and oil and gas pipelines to produce energy and move it around. And what's happening is we're moving to alternative energy sources. Rather than large grids, we're using microgrids. We're transmitting power in ways that we never before imagined. This is why the grid problem is a major challenge for engineers and scientists. And then ultimately energy storage so we can use it when and where we want. And these are all massive scale technology problems and policy problems. But what's changed is from the time I was a student to now is the price of wind and solar power has plummeted. I can look at this plot and see where I was in school, and the prices continues to drop low to the point where in a lot of places, wind and solar power is now cheaper than fossil fuel derived power, which it blows my mind that this is the case. And of course, with lower cost has come this explosion in the installed capacity of wind and solar, which you, as younger generation of students, you probably have seen large scale wind and solar facilities at this point that maybe people didn't see 20 years ago. So what's the problem here? I mean, we still have wind and solar power that's either carbon neutral or low carbon, and depending on how you count what goes into it. And on the other side of this, we have products now that can use energy in places where before we would emit carbon. So for example, now the Chevy Bolt MSRP, which I took from there, is about $36,000. The Nissan Leaf's about $30,000. So these technologies, both on the production side on the far left and the utilization side on the far right, are now at the point where they're cost competitive with conventional approaches, which to me is still amazing. So what's the last piece of this that we need to get to a fully decarbonized, sustainable world? And that's the technology that exists here in the middle. We have to be able to store energy. We have to move energy around. We have to balance out the temporal variations. And we have to make this an energy commodity that we can move around and trade where it needs to be in a capitalist system that's incredibly efficient. So what's the problem? Well, the new problems are different than the old problems. We have volatility. This is the temporal problem of energy. Energy needs can change from seconds to minutes, but also hours to days and months to years, right? Daytime and nighttime, as well as we use a lot of power in the winter and in the summer and less in the spring and the fall. So how are we going to deal with all of these timescales of energy production, energy storage, and energy utilization? And this is complicated also by the fact that we have a different dynamic energy system, right? Rather than just single locations of energy production, we can now produce energy at all sorts of locations, whether they be a large field of solar panels, whether they be a solar panel on top of your house, or a wind turbine that's in Nebraska, all sorts of different places. So what do we know about this? Energy can be created and stored at both large and small scales in this new energy economy. It's preferable to move and use power immediately rather than to store it because we don't have to pay to store it. That requires extra cost. And energy management requires all sorts of insights that we didn't have before, like data measurements, control strategies, optimization algorithms, and network security because of the internet and potential security problems with that. So we need solutions that go into this, and we have certain requirements that are going to play into this. For example, we'd like to use existing capital infrastructure. The United States and the world has already invested trillions with a T, trillions of dollars in infrastructure, in producing energy, supplying it to consumers. And what we don't want to do is eliminate all that and start fresh, right? We'd like to make an energy storage medium that's movable and tradable. So just like we have natural gas, we can put in a pipeline, petroleum, we can put in a pipeline. We would like renewable carbon-free energy to also be used in a pipeline or on a truck or in a ship, something like that. What else? We'd like it to be fungible. So I have it, I can sell it to you. I can put it on a truck and drive it over to you. I can sell you a ship of it. And of course, I'd like it to be cost effective. This is a picture here of actually, it's about 5 or 6 years. Oh, it's even older than that now. 6 years old government report on the cost of energy storage by a bunch of different technologies, whether it be batteries, hydrogen storage, liquid organic hydrogen carriers, LOHCs, or ammonia. So what's a solution to all of these different technologies? Well, of course, they're all probably going to work together. We're already using lithium-ion batteries for all sorts of applications, and the price of those keep going down, and there's all competing technologies. But you can see here, different technologies address different time scales. So batteries are really good for short time scales, but not so great for long time scales, and not great for distance either, right? I don't want to have to move batteries from Nebraska to New York City. And so effective energy management is going to require a mix of these technologies to make it work. And what I want to propose to you is that ammonia is actually the solution to a lot of our energy problems between the upstream production and the downstream utilization. It's that solution that exists in the middle. When you use ammonia as an energy source, you can use it many ways. You can convert it back to hydrogen, and when you burn that, you're going to make water. and the byproduct will be N2, which is already 80% of the air. Ammonia is very much like propane. It can be liquefied, it can be put into pipelines, it can be put into tankers and ships. And we already use it and store it, transport it in agriculture in ways that we've learned to deal with the toxicity of it and the safety issues. And it's incredibly energy dense also. So why would this be great? Well, let me give you a picture here of Minnesota. So if you're not familiar with Minnesota, we're one of the states up close to the Canadian border, which you can see up here at the top. This is the Twin Cities, Minneapolis and St. Paul in red on the picture on the right. About half the state lives in the metro area, and the other half lives distributed throughout the state. So we use a lot of power in a very small region. But most of our wind power, as you can see on the plot on the left, exists way down in the southwest. That's about a 4 to 5 hour drive away from the Twin Cities. So we have a lot of potential for sustainable renewable energy. It's just not anywhere close, and when we need it, for the Twin Cities where most of the people live. So what we'd like to do is take places that are stranded like this, where there's lots of energy potential, like the United States from North Dakota down to Texas, there's a lot of wind power. In Australia, there's an immense potential for solar panels. Same thing with the Sahara Desert. We can put wind and solar installations there, produce hydrogen, convert that to ammonia, and then we can put ammonia on a ship, just like we would with petroleum. And we can park that ship off the coast of Mumbai, off the coast of New York City, Beijing, wherever we want to use it, and then pipe it in and use it. And that allows us to move the energy from a rural distributed location to a place where we need power. So why can't we do this? Move to the next slide here. Well, the answer is we're already doing this at some scale and in certain applications. So the picture you see here, this is a picture of far out in western Minnesota. It's about a 3.5 to 4 hour drive, depending how fast you drive. I'm a slow driver, so it's 4 hours for me. Where we have the University of Minnesota Morris, one of our other institutions. And you can see here we have both wind turbines, we have solar photovoltaic array. And then in this little facility you see right there in the middle, we actually have an ammonia production facility where we're converting wind and solar power to hydrogen and then to ammonia. And then we use that in this location for agriculture, but we could use it for energy as well. So this is what our on-site production facility looks like at the University of Minnesota. You can see we make hydrogen, we store it, we have a nitrogen on site. We have a transformer to convert power to the voltages we need. We can store ammonia. And then the reactor is back here in this building you see in the background back there, back behind there. So why can't we do this everywhere? I would like to put hydrogen production and ammonia conversion all over the world and generate ammonia for energy storage and fungibility. And the answer is that the catalysts are not good enough. This is where we get back into the chemistry. The biggest cost of issues in ammonia synthesis and all related are related to catalyst performance. That goes for making hydrogen, but also making ammonia. And so we think about what the catalyst has to do here. The first step, like I said, is ammonia or N2 sticking to the surface by adsorption, then breaking apart. Then we add the hydrogens to it, and then it comes off the surface as ammonia. And usually the catalyst helps break apart the bonds that we would like to break apart at lower temperature. And in this case, 400 degrees C is about the best temperature we can operate this at and still get a reasonable rate at which we break apart nitrogen-nitrogen triple bonds. So even that is not that great because it requires such high temperature to do this. We really need a catalyst that works at lower temperatures and is faster overall to make this type of technology work at a smaller scale. So what's the problem? Let's see here. Okay, so let's take this reaction and we're going to break it into two parts. So let's take the first part. The first part is where nitrogen adsorbs to a surface and breaks apart. And what we would like here, I call it metal stickiness, but really what I'm talking about is what we call the adsorption enthalpy. What is the energy released when you bond that molecule to the surface and then break it apart? Now, obviously, if you bond stronger and stronger these atoms to the surface, they're going to more readily pull apart that triple bond. And that's what we've seen throughout history and in the way molecules behave on surfaces. So if on the plot on the right there in green, you can see that as I bind molecules to the surface stronger and stronger, the rate of reaction goes up, which is good. I like that. Now, if we look at the other half of this, now, once we've added the hydrogens and we have to get ammonia off the surface, if we bind stronger and stronger, eventually the slowest part of this whole process is not how fast we break apart N2, it's how fast we get ammonia off the surface and add the hydrogens on. So we end up with this essentially Goldilocks problem. We have two parts of the reaction in general. It's actually many small parts, but they each have to be balanced in terms of their rate. If you make one too fast, the other one slows down, and vice versa. And so what Fritz Haber really discovered 120 years ago when he won the Nobel Prize was that iron, the metal iron catalyst, sits right at the peak of this particular volcano, right there. And the problem is that peak, we call it a Sabatier limit, after a French scientist who put all this together and understood it in the 1960s, that we can't make a catalyst go any faster than the Sabatier limit, even though we are looking for things that exist up in that target region far up above. Now, the U.S. Department of Energy, the National Science Foundation, every catalyst company and processing company in the world would love to have a catalyst that goes faster than the peak of this Sabatier limit. We also call this a volcano plot because it looks like a volcano. That's the more informal name for it. So the peak of the volcano is the problem in a lot of catalysis problems. Okay, so I've known about this for a very long time, and I've been thinking about it for the past 15 years. And over the past 10 years, I've developed this method by which we can come up with a method to actually bypass the peak of the volcano. And you can see here, this is a Wikipedia page that describes it. In red down here, you can see the red volcano shape, and you can see in purple there the solution we're proposing. And I'm going to explain to you what this is and how we're working on it today. So if you're familiar with this concept of resonance, resonance shows up by many names in chemistry, but it also shows up in physics. There's a very simple concept in dynamics, especially undamped systems, where systems exhibit natural frequencies, and we can perturb them in many ways at a given frequency. And when those frequencies match, we have an accumulating energy. Now, if you're not familiar with this, think of something very simple like a pendulum or pushing a kid on a swing. Right, the swing, just like most all pendulums, they move at a certain speed, which is why we use pendulum clocks. But if, and I don't suggest doing this because the kids won't be happy, but if you push the kid at just the right frequency, they're going to go higher and higher. And if you push them at the wrong time, then you're going to push them off the swing. So the idea is that there are natural frequencies to real systems, just like there are in chemical systems. There's time constants. And if we perturb those the right way, we can achieve performance that hasn't been possible in any other way. So I want to do that with catalysts. So let's go back to this picture you see right here. The vertical axis here is the rate of reaction. So of course, I would like to go faster and faster with my catalyst. The horizontal axis is a metric for each metal. So each metal has a characteristic. This is the binding energy in this one of one of the molecules. I think it's the product. And I call it the metal catalyst stickiness here just to make it as simple as possible. But if I can make one metal change its electronic characteristics, I could slide left to right on this axis. I could be on one side, then on the other. You can see there in black the shape of the volcano, and in red there, that's the best I could ever do by any conventional catalyst. But if we're able to actually modulate the electronic characteristics of a catalyst with time, and if we do it at the right frequency, what we call a resonant frequency, you can actually exist thousands of times faster than any catalyst that was possible before. So we came up with this idea I came up with it, I don't know what year, but we published it in 2019. And the idea you see here is just a graph with a concept. And so what we can actually do is run simulations, just like you probably did in some of your courses where you did kinetic modeling. This is just a little bit more complicated than most kinetic models. But what you can see here, I'll start at the top here. The very top plot tells me how strong I'm binding molecules. So what I'm doing is I'm going to very strong binding to very weak binding, to very strong binding to very weak binding. The plot on the bottom shows how many molecules are on the surface. And what you see is that it goes from a surface that's fully covered to a surface where all of those molecules came off. So we're filling the surface, unfilling the surface, filling the surface, unfilling the surface. And every time we flip states, you can actually see the plot in the middle there what we call the turnover frequency. That's another name for the rate of reaction. I want that to be as high as possible. Every time I flip the surface, the rate of reaction goes way up. And then eventually I deplete it and the rate comes back down. And then I refill it and I exhaust the surface, and I get these spikes in reaction rate that go way higher than anything that's been possible before. Now, what we can do is say, let me average that. Let me take that data, and I'm just going to average the rate of reaction. And I can say, well, how fast was my reaction? That's the vertical axis here. Versus on the horizontal axis, that's how fast I'm switching that catalyst between strong and weak binding. Strong binding, weak binding, strong binding, weak binding. And you can see here, we're looking at a very complex behavior. In red there, that is the best I could ever do normally. That's that peak of the volcano shape. In blue, you can see here as I go faster and faster of switching my catalyst, eventually I get up here to this top region where I'm exhibiting catalytic rates which are 100 to 1,000 times faster than what I could normally achieve with a catalyst. And that's the goal, to make catalysts as fast as possible by some perturbation method at these resonant frequencies. So when I saw this simulation, when it matched my expectations of my intuition, this is when I got really excited and we started patenting a lot of these ideas so we could protect the intellectual property and commercialize this technology eventually. Okay, so the last part of this, of course, is this is a great theory. It solves a very important problem. But how do you possibly take one metal and make it behave like another metal? Because this is very similar to this idea of alchemy. I have copper, but it would be great if I could make copper into platinum for many reasons. First of all, platinum's worth more. But also electronically, platinum has more uses for a lot of things than copper. So that would be great. That's why it's in such demand. Same thing with rhodium. Rhodium is incredibly expensive, but we have a lot of nickel, right? Nickel is cheap and abundant. So what I would like to do is change the catalytic properties of these metals. And of course, you know a lot about chemistry from taking your chemistry classes. Chemistry is all about the movement and density of electrons. So what I want to do is I'm going to take the metals, atoms, you can see them here in the top, that's the catalyst. And what I'm going to do is I'm going to stabilize a large number of electrons in those metal atoms. And if you do stabilize enough electrons, you can actually almost change the oxidation state of that metal. And you can do it very quickly because electrons move around very quickly. Now, how do you get a lot of electrons to stabilize in one place? And the answer is you put its little friend next to it, a positive charge, and you put it as close as possible, and you put an insulating layer in between. And that creates a very powerful electric field between the two. So powerful that I can put in an enormous number of electrons into that catalyst layer. And when I do that, I change the properties of the metal such that it binds with molecules on the surface differently. Okay. So that's what you see here. This is a cartoon of the device. You can see here, we build these on silicon. And then on top of that, we do what's called atomic layer deposition. So we can put down single atom by single atom layer of hafnium and oxygen. And that's about 70 nanometers thick. On top of that, then, that's an insulator. So no electrons can flow through that. On top of that, then we put a single layer of graphene. So you can see here in the picture, the graphene. And graphene is good because it lets the electrons shoot really fast across that surface. And then on top of that, we put our metal cluster. So in this case, we use platinum. Now, my colleague here at the University of Minnesota is really good at electron microscopy. He took one of these devices and he sliced it. And now we're looking across the device. You can actually see it right here. See the G, that's the graphene film. And then the platinum clusters, which are a couple of nanometers in size, sit right on top of that. There's a couple of layers of particles here thick, but you can actually see the individual clusters of platinum. Now, what's cool about this is now I have a platinum cluster, which is a catalyst where I can tune the electronics of it. I can give it extra electrons, or I can take its electrons away and it'll have a net positive charge, depending on what voltage I give to that particular device. Now, what I'm going to do is I'm going to put carbon monoxide on it. Carbon monoxide is a really good probe molecule because it binds very strongly to platinum. And what I'm going to do is I'm going to raise the temperature slowly and linearly. And at some temperature, there's going to be enough energy for the carbon monoxide to desorb and come off into the gas phase where I can measure it. Now, if I'm changing the electronic properties, I'm changing the binding energy. If it binds stronger, I'm going to have to go to a lot higher temperature to manipulate that platinum, to get the carbon monoxide off that platinum. If I weaken it, let's say I put a lot of electrons in, it's going to bind the carbon monoxide weaker and it's going to come off at a lower temperature. So what you can see here, each of those peaks you see on the right there, those are the peaks of the carbon monoxide that come off the platinum surface. And you can see what I've done is I've tuned, I didn't do this, the graduate student did it. They tuned the voltage that this was done at. So you can see at 0 volts, we're right in the middle, that's just normal platinum. At -6 volts, I've pushed a bunch of electrons into the platinum such that I've weakened the binding with carbon monoxide. And you can see the peak is earlier in the plot. And over on the bottom now, you can see that for +6 volt, I've taken the electrons out such that carbon monoxide is putting more electrons itself into the platinum and binding a lot stronger, and it comes off at a much higher temperatures. So this is now what I want. I have a catalyst that I can just turn a knob and give it any state I want. And we've made these now so that they can switch states 3,000 times a second. Now at that speed, if a molecule is on the surface reacting, it might start out thinking it's on platinum. Halfway through the reaction, it thinks it's on another metal entirely because the metal is behaving like a different metal. So here's what's happening. This is why we call this programmable catalysis. We have a reaction, and I'm showing this as the simplest form. A goes to B, and when it reacts, it goes through a transition state in pink. The reaction is going to happen the fastest when I've removed the most electrons. So the most positive voltage, that's when all of the positive charges are there, that's when the reaction happens. Then I put the electrons back in, and I weaken the binding of everything, and they come off the surface. So when I say a programmable catalyst, the simplest program here is just a sine wave. Put it from one state to another, or a square wave. And that's the type of system that gives me really good catalytic performance. So why do I want this? If I can make reactors faster, I can make them smaller. And I can make them do all sorts of other crazy things I'm not going to have time to talk about. But what we could do then is take big displays or big systems like these wind turbines. We could put them in the middle of nowhere where nobody lives. And then next to it, we could have a tiny little reactor house like this that's converting wind power, water and air into ammonia, and then collecting it and putting it into a pipeline and shipping it to the coasts, and then putting it on ships possibly. We could do this in the Sahara Desert. We could then move ammonia to anywhere around the world we want. And if we need more in place, we could send more ships or take ships away, just like we do with petroleum. It would be carbon free. It would be liquid, so we could store it when we need it. We could have a strategic reserve. It could meet all of the needs we have right now with conventional liquid fuels. So let me just kind of summarize a few things here. I think small scale ammonia would change the way energy moves around, the way we store it. It can be moved between micro and macro grids, but it's going to require, of course, new technologies. We're going to require small scale reactor systems. They're going to have to be operated independently. All these are control problems. And of course, we have to think about the logistics of how this would happen. Where do we want to make the ammonia? Where do we want to store it? Where do we want to use it? How do we want to use it with our conventional wind and solar systems? So this is why we recently applied for and were awarded the Department of Energy Frontier Research Center, because what we're talking about now is a new field of catalysis where the catalysts are no longer just a particle or a surface. They're actually like a living, changing system that's changing on the time scale of the reaction. And so my students in my group, they make devices like this one here. This is, again, a cartoon. It's a computer drawing. The actual devices look like little computer chips. But what they do now is they put one of these in a reactor and they change the voltages that they send to this device to give it different properties with time. And of course, we need to understand how to design these devices, how the molecules behave on their surfaces, but also if I want to send it a signal, a program of how to behave, what is the best possible way a metal atom could change with time to control the chemistry? All of these are completely undeveloped because we've never looked at these problems before. And so there's all sorts of theory, computation, experiment, materials design that go together that makes sense to combine into a single center with 15 faculty working together. So let me just thank, of course, the people in the Center for Programmable Energy Catalysis. I'm the director of that, but a whole bunch of people all work together. And the US Department of Energy funds this research for the reasons that you see, both for the catalysis science in it, but also for the applications for energy storage and large-scale decarbonization. So thank you. Hopefully I didn't talk for too long, but I appreciate it, and I think there's plenty of time for questions.
Yes, there is. So Janelle, do you want to start off here?
Yes, let's thank our speaker for talk.
Yes.
And yeah, is there anyone who has any questions?
Actually, I do, Janelle. So I learned so much from this presentation. So are you then proposing, so one, question, are you now proposing us going from what was a big deal of like us trying to get to a hydrogen economy, and now you proposing an ammonia economy? How, when did this change happen? Was it with your ideas, or was it something, out there that others were talking about and you studied it and had a way to accelerate that? Because, we were all talking about hydrogen economy.
Yeah. So that's a great question. So there's a lot of facets to this. Number one is an ammonia economy is a hydrogen economy because we need hydrogen to make ammonia. So in a way, it doesn't change that at all. It just makes it easier to move and store hydrogen. And you can think of ammonia almost as liquid hydrogen, but it doesn't require the extreme conditions. Another part of this, though, is I showed you this volcano plot. Let me see if I can find this quickly. Here, I went right to it.
Okay.
This shape that you see right here, this exists for hundreds of reactions, including the key reaction to make hydrogen. So if you hear people talking about making hydrogen by hydrolysis of water, they talk about what's called the overpotential. They need to apply extra energy to make the reaction go fast enough. And that has to do with the shape of the volcano curve being too shallow. It doesn't go up far enough into the efficiency of the plot. So this technology, I talk about ammonia because it's the one that's kind of the easiest to understand. It also applies for things like CO2 conversion. It also applies for oxygen evolution, which is the key reaction for hydrogen production by electrolysis of water. Right. So I'm not just interested in ammonia. I'm interested across the board as a platform technology. Ammonia is one of the key ones. Hydrogen production is number two.
So in a way, because I remember that was one of the discussions with the hydrogen economy, is that how to best transport it, how to best move it around. Yep. And so your suggestion here is that ammonia is a carrier for the hydrogen.
Yes.
Okay. I see. Very cool. First time I'm hearing about it. Other questions? Anybody has their hand up?
Did we just jump in, or?
Yeah, just jump in.
Hi, I'm Robert Johnston. I'm down in Texas. I see that you survived a year at Dow. I managed to survive 32, so congratulations. Were you up in 1776 building, or?
I was. Yep, I did. Actually, yeah. I spent time there and in Freeport. Oh,
you were in Freeport. Okay, well, that's where I'm at. Great. I love the talk. Love the topic. I have some questions related to polymerization, but let me start with some other questions. And I don't want to hog the floor here, so I'll just ask a couple of them and then maybe come back. But first of all, what's the energy transformation efficiency versus conversion to hydrogen or storage in a battery?
So these are great questions. So the way I think about this is every time I'm going to change the catalyst state from one to another, and there's molecules on the surface, the difference in energy input is the difference in the enthalpy absorption. So we think of it as the delta H of that system. Now, what I would like to do is every time I have a reaction, only turn the surface over one time. So there's a plot I don't have on here because this is the introduction, like the basic introduction slides, but we can actually plot out the efficiency of these systems at different frequencies and different amplitudes. And there's regions and pockets that exist that exhibit very high efficiency. So you would operate it not just to give you good performance and speed, but good performance and efficiency. Now, there's other things that matter here, such as, with ammonia synthesis, there's a lot of energy that goes into the temperature control, which is very high temperature, but also incredibly high pressures of hydrogen, which is very demanding. And so one of the things you can do here is actually if you have a faster catalyst, you can operate at lower pressures. So it's not just the energy, which saves you a lot of energy in the conventional process. So putting this all together is where we're building towards. I can't give you a specific answer on what the total energy savings is, but that's what we're working towards.
And the catalyst site density compared to conventional heterogeneous catalysis, is it practical? I mean, you're obviously using kind of nanofabrication techniques to build these things, and it's great for demonstration purposes, but obviously natural, catalysts have, very high density of active sites. I mean, are you picturing this maybe being done in some sort of maybe, tubular reactor or something that gives you a lot of surface area, or how do you envision this working?
So just so the students understand, you're asking a very important question here. And let's see if I can get this to, I'm not going to do it easily there. Let's see if I can get there this way, maybe. Yeah, so just so the students understand, we're talking about 2D devices here. This is a surface. And normally in a catalyst, you have lots of micropores and nanopores, which give you incredibly high surface area per gram of material. And when we work with a 2D surface, we don't have that same number of active sites for the chemistry. And so what we're doing is we're designing, well, I'm not going to say everything because we have intellectual property we're working on with this, but we're working on strategies that can take these surfaces and expand them into high surface area applications. But you're absolutely right. It's a very important point. If you get higher activity per site, but you lose a lot of sites, you don't gain anything.
Mm-hmm.
Okay.
And then maybe the last question, then I'll take a break. But there was some work reported about a year ago. It was mentioned in the Chemical and Engineering News in an August article, but I think it was published in Nature by Simonov and McFarlane of Monash University. It was describing a very high efficiency electrochemical process for converting nitrogen to ammonia. If you got any comments on how this compares to that in terms of kind of the order of magnitude, expected, energy efficiency or cost reduction?
I don't have that because you're asking like the techno-economic analysis questions, and we don't, until we have the catalyst working and build a process around it, I won't have it. But these are absolutely the most important questions. I don't have the answer though. So
okay. I'll take a break and come back with a couple more.
Thanks. All right. Any other question from David? I saw you had your hand up.
Yes. Yeah. My name is Dave Novak, and I'm a biochemist, and I'm just curious. And I know you're an engineer, but do you see any? Have you or your team investigated this sort of a electrical effect that might be seen in the nitrogenase enzyme itself? In other words, the application of ATP or NADPH would change the electrical surface of the molybdenum or iron in that catalyst, and it's sort of like the way you're doing it, or where you're supposing to do it. Do you see any effect in the natural world in nitrogenase?
So that's a great question. I wrote a paper that was published yesterday that came out making the connection to biology, and I just put it in the chat.
Okay.
So I have been studying biology for the past 5 years, trying to understand what's the relationship between what we're doing and what nature naturally found over millions of years. There's all sorts of interesting behaviors with proteins, particularly things like ion pumps. Actually, I don't know, I'm going to hold this up as well. If you've seen this book, it's written by a guy from Wayne State, actually, just down the road from you. Where he, can you see it there? Okay.
Yeah.
Yeah.
Okay.
I mean, I'd have to blow up, and I can't see the title of it right now.
I'll put the link in the chat.
Life's Ratchet.
Life's Ratchet. I'll put the name here in there. But my point is that a lot of these phenomena that we see with the dynamic catalyst systems exist in proteins and biology already. And some of the weird behaviors we saw in our simulations, which I haven't shown you here, I was worried about publishing until I read about biology and saw that all of those behaviors already exist and are not breaking the laws of thermodynamics, which I was worried about, right? So,
right.
That is really cool.
Okay. One last thing. You're hoping to extend this knowledge of catalysis that you're gaining, the changes in catalysis due to voltage for ammonia, but you're hoping to extend that into the production of hydrogen from water. Is that correct?
That's right.
That really because that's what that's really the missing ingredient from what I've seen here is the hydrogen in these little micro production facilities next to these windmills. You have to both produce ammonia, but first you have to produce the hydrogen.
That's right. So we talk about ammonia a lot because it's very well studied in catalysis science, but it's a platform approach to break the Sabatier limit in general. It's a general approach, and the device is a platform. I can put anything on it I want.
Okay. All right. And you don't see any limitation for that. I mean, chemically between nitrogen and water. You don't. There's no behavior of those two elements that would prevent one from acting like the other, or what? I mean, you get what I'm thinking.
Yeah, it'll take a different active site, and it'll take a different electron density control, and the time constants are different, but we're modeling both of them and pursuing them both in parallel.
Okay.
I think our first goal is to show we can beat the Sabatier limit. That's like breaking the speed limit in I don't know, but it's never been done before. So our excitement is to show that it's possible. So
I've always been highly skeptical of the hydrogen economy simply because of the difficulty of managing hydrogen gas, how explosive it is, how tiny it is, how hard it's going to be to capture and keep. And I really like the idea of connecting it with ammonia. While it's toxic, it's I think in the grand whole scheme of things, not much more toxic than gasoline is.
Yeah.
Once you manage it well. So I wish you very well. I hope this works.
Yeah, I for many reasons I hope so. I think the Department of Energy has talked about how hydrogen right now by electrolysis costs $7 to $8 a kilogram, and they want to get down to $1 to $2 per kilogram. So I think I appreciate that they're funding us because we're going after something very unique, and it could be. We'll see how it turns out, but I think there's a lot of promise in it.
Right.
Dr. Randall, I think I saw your hand up too.
Yeah, it's very interesting to hear about this, and I mean, it's really cool to basically be able to, in real time tune the properties of the metal, right? Which is, it's alchemy, but dialing it back and forth, right, so to speak. So, anyways, and you don't even have to boil gallons and gallons of urine.
That's a plus. That's a plus. Or move manure around the world. So
yeah. So my question was, in that data you were showing, that was like the CO absorption to the platinum surface at the different potentials. You were doing C13 CO, or you were looking at it. Why C13 and just not regular?
It has to do with the mass spec detection. We wanted the peak to not overlap.
With nitrogen.
With nitrogen, that was potentially in there. So
yeah. Okay. Gotcha. Okay. So you had to bite the bullet, and that's the cheapest isotope of C13.
It was the easiest way to detect it readily. So
yeah. So the other kind of question was, so like with fossil fuel, it's already in the burning form, right? But with this, basically what you're doing is you're having to invest energy to turn it into ammonia, and then you get the energy back out when you convert it out of ammonia into nitrogen and hydrogen or whatever, or water, I guess.
Water. Yeah.
So how does that? So I mean, it decreases the quotes efficiency of the overall system because you have to put energy in and then get energy back out.
Yep.
So help. And I mean, if the energy you get out in the end is more, then it's okay.
Yeah.
And it's a net win.
I'd say you're absolutely right. There is a penalty to convert it into ammonia and then take it back out. I would say that it's not that significant in the sense that people are already doing this. Shipping is a big target for this. Companies want to be able to put ammonia on ships and use that instead of fossil fuels. Also, in the Middle East, they're already doing what's called blue ammonia. Ammonias are identified by many colors. Blue ammonia is where they make ammonia from fossil fuels, but then when you use it, it's carbon free. So I agree with you. It's unfortunate, of course, but it solves some problems. It hurts you in your efficiency a little bit, but it's not to the point where it'll prohibit this approach.
And then with using, renewables like solar energy or wind energy, you're getting, I mean, it's basically energy that was getting quotes wasted or unutilized before anyway. So in this sense, it's free to make.
Yeah, low cost. Yeah, but still, as an engineer, right. We like to optimize everything. So sure. I get the point. And you can't do an analysis, life cycle, techno-economic without accounting for all of these things and making a fair comparison.
Yeah, I wasn't trying to criticize it. I was just trying to understand. I mean, it's a great idea. So, and we were just doing a nuclear energy in our general chemistry class. And so my big speech to my students, maybe some of them are even here, was, this energy problem is something that we really have to solve as humanity. So to your point about, making, we have another big technological development that we have to do in our society. So anyways.
And I think it's fair to try to criticize all of these things, right? Because criticism, if it's constructive, helps us figure out the problems, helps us avoid pursuing bad ideas. In academics, we like to think we're good at accepting criticism, but not always. So we do our best.
So agreed.
So I see Colin Cha. Is he still online? You have a question in the chat. You could unmute and ask the question. Colin? See, not there. Well, I'll go ahead and ask the question for him. Is this reaction only possible at high temperatures, or are there catalysts that reduce the temperature for the reaction?
So that's a great question. And I think for a lot of so if we can make a catalyst that's faster, we can operate at lower temperature, because the temperature is what's driving the rate of reaction in a conventional catalyst. So the question is that what we want out of the final process? If we have the ability to go faster or reduce the temperature, or which one of those makes more sense for a small scale application? So the answer is you can go to lower temperatures if your catalyst is faster.
So I noticed that you use, platinum as sort of like the test model here, but I'm assuming at the center, you guys are going to be testing a wide range of metals, correct?
Yeah, that's right. Platinum has been so well studied by surface science for 50 years. And because we're trying to invent new devices, we don't want to look at too many new things at once.
What about, have you started working on iron as a catalyst?
Iron, copper, and nickel are three that are very interesting to us because they're all low cost and abundant.
Right. That's what I was thinking. Yeah.
Yeah.
Okay. All right. Couple more questions possibly here. Robert, do you want to ask another question, at least one more?
Sure. You're working with small molecules, so I'm assuming diffusion is not rate limiting, and you're controlling, so what you're doing works because of that. Have you considered looking at, I mean, if you were to apply this to a heterogeneous polymerization process, I'm guessing we'd start to deal with some issues where diffusion becomes a problem in terms of really effectively applying this kind of a technology. Obviously, in my field, which was polyolefin development, polyethylene and polyolefin elastomers, I wasn't working in catalysis, but I was very familiar with the work going on there. And obviously, we moved into homogeneous catalysts for a number of reasons, which have a number of advantages. But Have you thought of ways in which you could apply this to homogeneous catalysis by applying some kind of alternating electromagnetic field in a solution to a catalyst that maybe contains some kind of metallic component?
I would say that I have talked to my colleagues, and that because homogeneous catalysis is frequently done in chemistry departments. Not always the case, but I've talked to them about how we could do it, and we've been working on some ideas, nothing we've published yet. There's no reason the concepts that are here couldn't be applied to a homogeneous catalyst. It's just that's not my expertise area. Of homogeneous catalysis requires a lot of expertise to understand structure and characterization. So I think the answer is yes, it can be done, but I'm not doing it. My collaborators here, colleagues are.
Yeah. Okay.
Well, it makes sense that you're working with a stable metal and a simple system relatively in order to build up the technology. That totally makes sense. But the potential obviously expands greatly as you move into homogeneous space. I'll also just throw one closing comment in here. I took a class about 20 years ago or so in what's called TRIZ. I don't know if you're familiar with it. TRIZ. It's an acronym for the theory of inventive problem solving in Russian. It's the acronym is TRIZ, but it was some work that was done by a Russian patent clerk about 100 years ago, I think, in which he studied hundreds of thousands of patents in the patent system and came up with classifications for studying how the different technologies evolve. And the natural endpoint for many technologies is application of fields, very generically. And that's really where you're taking catalysis and a controllable field applied to the catalyst site. And I think that's a sort of a natural evolution of the technology, and you're following that path. So it's just an interesting kind of historical point, maybe.
I found this on Wikipedia. I'll check it out. Thank you.
There's an outfit in just Detroit area that's been doing a lot of consulting with the automotive industry and applying that, and also a number of other clients. But that's who I studied with. Ideation International, I think, was the name of the company. So anyway.
Cool.
So I would say let's ask Janelle to say thanks, kind of close us out, and then followed by Dr. Randall, our chair, to close us out for this school year of ChemSem. So Janelle?
Yes, so let's thank our speaker again for coming to speak with us.
Yes.
And
very good, very good. Thank you,
I'll
Janelle.
turn it over to Dr. Randall.
And Dr. Randall, you could just say a few words for us to close out 20.
Yeah, so basically this is the end of our chemistry seminar series. This school year's edition, probably about 20, a little low 20s, 22, 23 different talks on a wide variety of subjects, all touching on chemistry. But since chemistry is kind of central, we're a little biased, but chemistry is very central to human existence, from biochemistry to some pretty exotic physical things. I think our most exotic one was the helium-3 refrigerator and time crystals.
Quantum time crystals, man, that blew my mind.
But I think we've had a nice representation from different areas and applications of chemistry, just in terms of the basic research, research applied to solving important projects like we had today. We've had people talking about, interactions or intersections between chemistry and science and theology and neuroscience. And so we've really, I've enjoyed the wide variety of presentations that we've had for our ChemSem. And so thank you, Professor Dauenhauer, or Hauer, sorry, for closing out our presentations and for helping us understand a little bit more how ammonia can get used as a fungible fluid, energy fluid. So thank you very much. Thank you to all the students, and thank you to Dr. Murray for arranging our slate of presenters.
Very nice. Thank you very much. Thank you. See you guys. Take care.
Thank you.
All right.
So Andrew's, yeah.